I am going to discuss with you a very interesting example for calculation of deflection at tip of a cantilever beam. The cantilever beam is AB, which is subjected with a concentrated moment M, and we are going to find the deflection because of this concentrated moment. Now, uh, in next lecture, we will be solving cantilever beam, but it will be having varying moment of inertia. The beam will be like this. There will be a beam here. This kind of beam will be here. There will be a moment M, but here moment of inertia will be I, and here will be 2I. And total length of this beam will be L, as I am dealing here with. But here the moment of inertia is constant, I. And here half of length will having a moment of inertia I, and half of length will be having a moment of inertia of 2I. It will be this example will be solved using module 2 but lecture 10. You can see in our next lecture for calculation of deflection delta V. This is point B, this is point A, and here deflection will be something, and this value will be calculated in our next lecture, lecture number 10 for module 2. Now come to our solution for a deflection for a concentrated moment which is acting at the tip of a cantilever beam, and I am going to solve deflection using moment area method. Now the problem statement is here. Length of this beam is L, and the fixed support is designated with A and free end is with B, and at free end you can say at point B there is a concentrated moment M is acting and we are going to find deflection delta B here, and we will be solving this example using moment area method. As per the moment area method, as you know, deflection delta is calculated as product of area of M over EI diagram and centroid. You can say deflection delta B will be calculated area of M over EI diagram multiplying with its centroid of the same M over EI diagram. Now we need to find the bending moment for this beam, which is subjected with a concentrated moment M. Thereafter I will be developing M over EI diagram for the same beam, and after that we will calculate x bar, centroid of this M over EI diagram, then multiplying with the area of M over EI diagram with x bar will give directly the deflection at point B. Now here the beam is this beam is subjected with moment M, and this point support end is A and free end is B. Here we need to find the general expression per moment. Let's see a section XX. Let's take a section XX here at a distance of x from point B, so that we can generate a general expression per moment, so that we can draw a moment diagram, bending moment diagram. Now let's we have taken a section XX at a distance of x from point B, so we are taking a free body diagram. Let's separate out from left of this section. It will be something like this. the free end will be B, subjected with a moment in anticlockwise direction. Here M is acting. Now we want to find a moment here. Here I want to find a moment. Let's say this moment is mxx, because we are going to find moment at section xx. So what will be the moment? This is a free body diagram. Free body diagram. As you can see, in this beam that we have taken as a free body diagram, there is no any external load acting over this beam, neither concentrated load and point load or UDL or triangular or trapezoidal. Not any kind of load is acting on this beam, but there is only a concentrated external moment is acting here at point B. So as we know, we want to take moment at section XX. Let's suppose this is D. AB, you can say this is C, this point is C. We want to find moment at C. So we can say moment XX at section XX, or you can say a moment at C will be what? So that we will generalize this bending moment throughout the length of this beam. Now let's continue here. Let's continue with the free body diagram. Free body diagram is here. This is the beam, free end is B, and this section is XX. Section is XX, and distance is taken as this section XX has been taken at a distance of x from point B, and I have designated this point with C here. Now only loading is acting here is, this is the moment, external moment is acting on this at the end of this beam. This is the concentrated moment and we want to find a moment here at C. MC I want to find out here, and as per our assumptions, we are taking anti-clockwise moment as negative, anti-clockwise moment as negative. So we can say this is the anti-clockwise moment, it will be negative. As we know from the conservation of moment, the sum of moment through any point is 0. So sum of moment will be 0. So we want to about any point will be 0 because we want to find the moment about point C. So sum of moment about C will be 0, and as we can see here, about this point C there is a moment M which is acting in anti-clockwise direction, so it will be with negative sign, which will be minus, and MC which we want to find out, which is in clockwise, as I have assumed it will be acting as a clockwise, so we are going to write it MC, but there is no any loading acting in this beam, neither point load, trapezoidal load, triangular load or any UDL, so no other moment will be creating at this point because of other external loading, so it will be just 0. So you can see here MC will be M. So you can say MC will be M. Here the beam is, you can say the problem statement is here. This is the length of this beam is L. Moment is here acting as M, and we have taken a general section XX at a distance of x from point B. This point is A. and we found that at any distance x from point B, a moment is m, and we can, if we take this section throughout this length, the moment will be same because it is not going to vary, because with the MC is finding out constant, it's not a function of x. So we can say moment is constant here. So we can say moment is constant throughout the length of the beam. Moment is constant throughout the length of the beam. Throughout the length of the beam. So from free end to a fixed support, the bending moment will be constant, having a constant value of m. So you can draw. So we can draw a bending moment diagram here. At C, this is the moment here acting is of value m. At section xx, this value will be same, and we are not finding it with any function of x, so it will be of constant value. And this point is B, this point is A, this point is A, and this is the moment value m at the support, and at free end there is the same value, and we have generated a bending moment diagram. This is the BMD. Now as per the moment area method, we need to find a m over ei diagram. It means every y coordinate, I mean this m coordinate will be divided by a constant value of ei. So it will also be a, this is the m diagram, you can say bending moment diagram, or m diagram, you can say it's a m diagram. Here I am writing again, this is the m diagram having a value of m, length is L, and this point is A, this point is B. This is M diagram. Now M over EI diagram of the same beam will be, but as we are going to divide M, I mean bending moment is divided with a constant value of EI, so its value will be somehow smaller than this, so it will be the M over EI diagram. Here it will be M over EI. So this is the M over EI diagram. Length of this beam will be same. This value is M over EI. Now this is the rectangular shape having base length L and height is M over EI. So area of this M over EI diagram, area of M over EI diagram, area of M over EI diagram will be base length multiplying with height will give the area. It means L multiplying M over EI. You can say ML over EI. This point is A, this point is B. The point where we want to find the deflection, or from that point, that will be the benchmark, and from that point we need to find centroid of this M over EI diagram. So centroid of this EI diagram will be center, because this is the rectangular shape. So centroidal distance x bar will be at a distance of half of this length, L by 2. So x bar equal to L divided by 2, half of this rectangular shape. So x bar of this M over EI diagram will be L divided by 2. Therefore delta, as per our this is the area of M over EI diagram. Delta will be A multiplying with x bar, area of the M over EI diagram, and x bar the centroid of the M over EI diagram. A equal to area of M over EI diagram, and x bar equal to centroid of EI diagram, over EI diagram. Now delta will be A multiplying with x bar. In place of A, we can use this value, that will be ml divided by EI, and in place of x bar we can use a value, this L by 2 it will be here, so it will be ml square divided by twice EI. So deflection will be ml square divided by twice EI. This is the deflection value calculated at tip of this cantilever beam, which is designated as delta B, because we have found out the deflection at point B of this cantilever beam, which was subjected with a concentrated moment of value m. And I will be coming with the another lecture for calculating deflection at the same point B of a cantilever beam, but it will not having a constant moment of inertia. Here moment of inertia will be of different value. After a certain length it will be changing. So we will be discussing this example in lecture 10. So I hope you find this lecture very interesting, and we will be covering this kind of examples having a concentrated moment. Thanks for watching. Thanks.